Okay, so today we're going to continue with what we talked about last time. We introduced the Laplace transform. We figure out how we can find the direct Laplace and the inverse Laplace via the linearity property and the table of formulas that you should have in front of you. And toward the end of the lecture, we provided an example of how to solve a differential equation using the Laplace transform. So this lesson is basically focused on that. We're going to go over more examples on how to apply the technique to solve linear differential equations. Once again, you should have the table in front of you, the Laplace table. And if you still have questions or misunderstandings related to the first part of the chapter, just go back to the lecture notes or the video lecture to make sure I understand completely how the mechanics works in this chapter, especially the part of taking the Laplace transform or the inverse Laplace transform and how you manipulate that table. So what I wrote here is basically what you have in the table of formulas. You don't have to write it down, just have in front of you. I put it here just to have a quick reference. Now the table of formulas contains more than these Laplace transforms, but these are the ones that I'm going to use in this presentation. So the key formulas that we're going to use in solving linear ODEs are the Laplace transform for y prime and y double prime. Why? Because, well, we focus on solving first or second order linear equations. There are more tables of formulas with Laplace transforms of derivatives of any order. So you could use basically those tables if you ever have to solve higher order differential equations. But in this class, again, we focus only on order 1 or 2. So before we proceed with the first example, notice carefully here how the formula for L of y prime and y double prime is in terms of the initial conditions. So you have to make sure you plug them in the correct position. Y of 0 is by itself in L of y prime. Y of 0 is times s in L of y double prime, and y prime of 0 is by itself. So that's the first thing to keep in mind. And of course, to use the linearity property correctly before you actually apply these formulas. So what's the method is supposed to work? I mean, the first step is to apply the Laplace transform on both sides of the ODE. Use the linearity property and then carefully solve for big Y. So remember, big Y is the Laplace of little y. Remember the convention of notation that Laplace of little y of t is big Y of s. Again, for convenience and so that we won't waste too much time, we can drop the argument here of t or of s. Little y depends on t, big Y depends on s. So without further ado, let's tackle this first example. This is a first order ODE. And so if you want to do it with the Laplace transform, again, the first step is to apply the Laplace transform on both sides. Then linearity property. Now try to do this in your mind. After a couple of examples, try to speed up this process. So for example, this distribution of the Laplace transform, you could do it in your mind and go right ahead with plugging in the formulas for Ly prime and L of e to the minus t on the right hand side. So L of little y prime is s times big Y minus y of 0. Be careful here, it's a double negative, right? So minus y of 0 is minus negative 1. And then plus L of little y, which is big Y. And on the right hand side, of course, is the Laplace of e to the minus t, which is, according to the formula here, 1 over s minus negative 1. Again, because little a in the formula is negative 1. Be very careful how you tackle these negatives, because there is a negative as part of the formula, but a itself is minus 1, hence you have a double negative, which makes it 1 over s plus 1. From this point on is just algebra steps to isolate y. Okay, so the step number 2 is to find big Y. Y will appear on several positions, but it will appear always at power 1, which is again the beauty of the method, right? I mean, all of these Laplace transforms will give you a big Y times some other coefficient. So to solve for Y, it's just a matter of factoring Y out of all the terms where it appears, moving everything else to the right hand side. Here I have plus 1, and to the right hand side becomes minus 1. And plus 1 over s plus 1. One thing to keep in mind is to not really rush to combine the fractions on the right hand side, because it's possible that you already have a match with the table of formulas. So notice here, you could combine this if you want, but let's actually divide by s plus 1, right, to solve for big Y, and leave those two fractions separated. So minus 1 over s plus 1. And this is 1 over s plus 1 over another s plus 1, which makes it 1 over s plus 1 squared. The reason it's not, it's not worthwhile to combine it right away is that if you look carefully, these two entries, these two terms, already match the table of formulas. This is obviously matching an exponential, and this one, if you look carefully, matches this formula. Which is the Laplace of t to the n e to the at. So in your case, if you look carefully, a is minus 1 for that formula, and n is 1, right? Because n plus 1 stands for 2, n factorial is 1 factorial, so n is equal to 1. So when you take the inverse Laplace, which is the last step, right, to find the solution, little y of t, we take the inverse Laplace of big Y, minus 1 over s plus 1 plus 1 over s plus 1 squared. Make this thicker a little bit. So when you do that, you can apply the formula, the table of formulas right away. So this will be minus e to the negative t and plus t to the 1 e to the minus t. So that's going to be t e to the minus at. Okay. And that's the answer to this example. By the way, if you do it by classical methods, you would recognize it that this is actually an exponential constant e to the minus t, and the particular solution is with the extra t because of the duplication between the particular solution and the between the non-homogeneous term and the exponential part of the ODE, the homogeneous part of the ODE. So that's a first order ODE. Let's actually go over now over a second example, and where we have a second order ODE. So suppose we have y double prime minus 4y prime plus 3y equals 0. Now, one thing that people sometimes get confused is this 0 on the right hand side. When you take the Laplace transform, that's just 0, right? Remember the definition of the Laplace transform. Write it here. When you have that integral, e to the minus st times the function in the integral. If the function is 0, obviously the integral will be 0. So let's take the Laplace transform on both sides like we did before. So we have like the first step, right? L of y double prime minus 4y prime plus 3y equals L of 0, which, as I said, is equal to 0. And again, you can do the linearity property in your mind, but let's just do it one more intermediate step. So linearity property means we distribute the Laplace transform and we pull out those constants. So Ly double prime minus 4L of y prime plus 3L of y equals 0. So L of y prime is going to be multiplied by 4. So again, you have to be careful how you plug in these formulas. I forgot to specify the initial conditions, which we obviously need. So y of 0 equals 2. So let me write them here. Y of 0 equals 2 for this problem, and then y prime of 0 equals 0. Okay. So L of y double prime what does that mean in my case? That's s squared big Y minus s times y of 0, which is 2, minus y prime of 0, which is 0. Then minus 4, and I have to use parentheses here because in this parenthesis I'm going to throw in this L of y prime. All right, so s big Y, and then minus y of 0, which is again 2. Okay, so notice y of 0 is by itself here, and here is by multiplied by s, because it's part of the other formula. L, don't forget this guy, 3L of y, that's 3 big Y equals 0. So very carefully go over this computation, because if you make a computation mistake here, obviously the answer will be wrong. Now let's expand this and put together the y's. So we have s squared minus 4s plus 3 times big Y, and the remaining terms are minus 2s, which we move it to the right hand side. That makes it 2s. Here we have plus 8. Move it to the right hand side, that's minus 8. Okay, so furthermore, now we're going to have to probably use partial fraction decomposition when we solve for the inverse Laplace of y. This can be factored, so if we get y by itself, which is 2s minus 8 over s squared minus 4s plus 3. Alright, this factors into 2s minus 8. Let me get actually the other one. 2s minus 8 over s minus 1, s minus 3. I think the other pen is almost over. I wish it had an indicator. So 2s minus 8 over s minus 1 times s minus 3. Okay, so remember from last lesson, we cannot find the inverse Laplace right away because it doesn't match the table of formulas. We have to patiently split it into partial fractions, which in this case is a over s minus 1 plus b over s minus 3. So combine the numerators, combine the fractions, a times s minus 3 plus b times s minus 1 over s minus 1, s minus 3. So the numerator must match, and that makes it 2s minus 8 equal as minus 3a plus bs minus b. Okay, so form the system in A and B, so the coefficient of S must agree. The coefficient of S comes from A plus B on the right hand side, and that's equal to 2. And then the constant term minus 3A minus B must be equal to minus 8. Use elimination. In this case, you can just add the 2 to eliminate B. That gives you minus 2a equals minus 8 plus 2. That's 6, minus 6, and then a is equal to 3. Then plug in 3 in the first equation, for example. 3 plus b equals 2. And so b equals 2 minus 3, which is minus 1. Okay, so with that being said, that means big Y. Now you're ready to find finally little y, right? So big Y is going to be a over s minus 1, which is 3 over s minus 1, and then minus 1 over s minus 3. Like I told you before, if you remember in the previous lesson, if the factors at the bottom in a partial fraction are linear, like that, so with power 1, then you always end up with a bunch of exponentials, because you always split it in fractions like this, and they all tied up to the L of e to the at. So when you take the inverse Laplace of these terms, this is 3e to the t minus e to the 3t. Again, by classical means you will do it much faster. you can tell it right away that the characteristic roots, if you solve by classical means, over here will be r equals 1, r equals 3, right? So I mean, it's not a surprise that we end up for a homogeneous ODE with a combination of e to the t, e to the 3t. Again, you will see in the next lecture where the Laplace transform shines, so to speak, because it's not used for problems that can be solved faster by classical means. But when you have far more complicated or especially discontinuous functions on the right-hand side, this is when the Laplace transform works very well. These examples are just to learn the technique. Because more often than not, especially first order ones, can be done faster without Laplace, so by classical means. So stay tuned for the second part. I'm going to go over one more example and finish up with some other examples of taking inverse Laplace transforms, some of the more challenging maybe examples, and then we're going to continue after that with actually the most important section of the chapter, which you should allocate probably 2 days for it, although I'm going to present it in a single lecture with multiple parts. So stay tuned for the second part.